So this presentation on rainwater harvesting certification was given to the CanWest Horticulture Conference on September 29th and the Living Waters Rally on September 30th. My name's Ken Nentwig. I'm a retired landscape architect and also a registered or approved AP instructor with the ARCSA group, American Rainwater Catchment Systems Association. My background is University of Guelph Ridgetown campus. I'm teaching currently with Gaia College, with the CanArm and ARCSA groups, and with Pacific Design Academy. I want to start with two premises. One is that rainwater harvesting is good. And the other is that rainwater harvesting is a specific area of expertise. And as we go through this to show how things are changing and happening very rapidly in our world, in the realm of rainwater harvesting. The Paulus project has just published 5 water challenges to define British Columbia's future. I've taken a paragraph and it talks about the problems, drought conditions, issues demanding urgent activity, being proactive and preparing for the future, before there is crisis situation. And so all of these together are kind of the focus of my relationship with the rainwater harvesting and how this fits into the Paulus project. Now the top ones here, that problems are accelerating, there's drought conditions, these are obvious and noticeable. Everyone talks about it, it's in the news, it's everywhere. When we look at the issues that demand urgent attention, we can sometimes say, what can I do? What should we do versus what can I do? And then there's not just I, but what about we and what about they? And all of these different forms of the question come up. Then we also ask the questions, what do we do? What do we consider? What do we need to know yet and learn? All of these things kind of come out of that. The issues demanded urgent attention and action, but where do we go from here? And yet there are things that are happening. This conference on Living Waters Rally, the Watersheds 2016, Rainwater Day at the CanWest, the legislation changes, discussion and education, these things are underway. And we're looking now at specifically the new rainwater industry that is developing awareness and education, training, accreditation, and certification in this very, very specific area of expertise. We're going to start with the knowledge that roughly half of our potable water currently goes to outdoor or flushing, and we can change that by using rainwater to fill that. One of the things we have to face is that there are many, many groups, many different aspects, many different facets and faces to rainwater harvesting, and it just covers so much ground. That makes it complicated, and being able to work within those regions, within those rules and regulations to help develop new ones. And as the Paulus project breaks down into 5 main topics, leading to discussion and action and leading into the future as they have been doing over the past while. It's really, really good to see how this is developing. I want to make the case that rainwater harvesting will directly address 3 of those areas for sure. The insert says, he says it's rainwater harvesting. We have organizations. One I work with is CanArm, Canadian Association for Rainwater Management, bringing awareness, educating, conducting research across Canada in rainwater harvesting and best practices. So this is kind of the north of the border aspect. The south of the border aspect, but also international, is the American Rainwater Catchment Systems Association, promoting sustainable rainwater harvesting practices. And they are leaders. They've been doing this for over 20 years. And so we're working with them to bring education and training here into Canada. So where we used to have pristine nature, environment, we now have modified that dramatically and taken what rain falls on the land and on our roofs and put it into the storm drains and pushed it off someplace else. Rainwater harvesting wants to address the drought and flood resistance aspects by saying, let's interrupt that flow from the impervious surfaces and runoff going to the storm drain. Let's interrupt that and put it into rain gardens. Let's use pervious pavements and put that water back into the ground. Those types of things. When we consider that, there's also, in the landscape sense of things, using less water, conserving. Using drought-tolerant plants and using no lawns, or using dormant lawns, letting them go dormant, not using as much water. For rainwater harvesting, specifically in those areas, one, it's an alternative source. Two, we can practice detention, where we're holding water back on the site and not rushing it off into the storm drains. And three, retention, where we're putting it into the ground. Now, further to this, we can also add cisterns or tanks above ground or underground and use that same type of system, store more water for later use when we don't have the water available to be used for the various aspects we want to. This way, we're improving also on the detention aspects quite substantially. Rain gardens do as well by absorbing water like a soil sponge. Water for nature is another aspect that we could look at. The pervious pavements, of course, and the infiltration into the ground. Planting trees is a great way of keeping water in the environment rather than pushing it away someplace. It goes back into the environment through evapotranspiration. Trees also, and plant material of any kind, really helps water get down deep into the ground. Mulching planting beds so we don't have evaporation, using sheet flow and on-site infiltration. And of course, evapotranspiration is big because nature's cycle is water going into the atmosphere and then coming back down onto the built environment and the natural environment. So again, we have the alternative source. We have detention, retention, and infiltration in many different manners: rain gardens, bioswales, infiltration pits, and pervious pavements. The overflow, of course, goes to the storm drain or to some other storm system that has already been there and usable. Also, again, tanks can be added. When we look at water quality protection, the water in the cisterns is treated slightly, filtered, so that it's pure and clean as much as possible. That allows it to sit for a long period of time, and that protection just keeps it clean. In the landscape, we can eliminate chemicals. We can reduce runoff volumes. Again, the pervious pavements are a good option for that. We still have our alternative source, so we're not using potable water. We are detaining the water and protecting it from contamination, and then also we can go on further and we can use rain gardens, bioswales, infiltration pits, and get the water back into the soil. But we're managing that water, and we're not allowing it to receive and carry with it contaminants that are bad for the environment. There are other uses, too, for rainwater. As an alternative source, the detention factor before it goes into the storm drain, just by itself, stormwater management. And then other uses such as irrigation, flushing, fire suppression, potable uses, and so on. There are even more in a commercial sense or an industrial sense. So there's a good case, I think, being made for rainwater harvesting, the wise management of the catchment, conveyance, storage, and distribution, which can overall benefit the environment, reducing runoff, reducing associated pollution, erosion, and wastage of water, reducing the demand on potable water sources, and increasing water volumes returned to the soil. There's a good case for rainwater harvesting then being one of the opportunities to work towards meeting those goals that are challenges for British Columbia, but elsewhere in the world as well, and particularly across Canada and most urban centers. Premise 2 is that this is a specific area of expertise. It crosses over multiple trades and professions. Even though it's old as human habitation is, people have been doing this for ages. It's not rocket science. We've pushed it aside and centralized and controlled our water supplies and our distribution and collection of water on the way out, wastewater. Best practices for rainwater harvesting need to be applied. It isn't just anything goes. There are better and best ways of doing things. So let's look at what exactly a rainwater harvesting system looks like, and there are a number of examples out there. This being one that perhaps is a little funny to watch, interesting. I think it does work, but it is not what we're talking about. Here we see some more commercial and residential aspects, and they are substantial. So the large tanks on the upper picture and the bottom picture collect a lot of water and store a lot of water. In the residence there, it's not just a rain barrel, it's a cistern, it's a tank that allows much more water to be stored. And it comes in all sorts of shapes and sizes. This one, I believe, is out of the UK. But where do we start? The American Rainwater Catchment Systems Association a year ago, almost a year ago, published their first rainwater harvesting manual. There are 10, maybe 12 now trainers approved for across North America. There's an instructors group that manages the operations of what is being taught and how it's being disseminated. There's an education committee under which this group operates. There's an executive director and a board of directors that manage the whole overall operation into which education fits. In this program, the Accredited Professional AP workshop, the 2-day workshop, the course of study includes such things as supply and demand and pumps and controls and catchment and conveyance on rooftops, extreme conditions, hydraulic calculations, and on and on. You can see the list there. In addition, there is climate change, there's regulations, codes, standards, guidelines, the best practices which are outlined to say this is the best ways of doing things based on practice, but also based on the knowledge that we need to protect our environment. What about data sources, and where do we get the information to design and build these systems? What about the networking through the organization? And then on to accreditation and certification, which means individuals are aware of and know what they're doing. At least they have been tested to a certain extent to understand and to know those things. The process of design in landscape or in building a car, or designing furniture, all the same. And so this is the process the process of design in rainwater harvesting that is used is very similar. A system overview, a site analysis, a design principle, design approach, and then specifications and an owner's manual. But the first section really is answering the question of why. The aspects of the rainwater harvesting system to be considered, its feasibility, its initial calculations, what is the meaning of it? And I don't mean to use the word what there because it comes later, but are we doing this for irrigation or for flushing or for laundry or for potable service purposes or for fire suppression or stormwater management is really the why, because it leads into so many other things such as the what. The what is the natural and man-made structures. It considers now climate and the soils and the slopes and neighboring sites. It considers what will work and what won't work and what types of systems, because there's more than just one type of system to work with. And the what is kind of the details of the concept of all the parts and components in a kind of a larger scale. Has it got tanks, or are we going to use bigger cisterns? Are we going to be above ground? Are we going to be underground? Do we have to worry about frost, and how much water can we collect? How much water do we need to collect? And be very precise about those things. The design approach is the how, and now it talks about the exact details, number of fittings, number of 90-degree angles or 45-degree angles, number of connectors, lengths of pipes, materials that are being used for the tanks or the cisterns, how things will be constructed, all the specifications that goes along with it, and then also the owner's manual that says here's what to do with it now that you got it, how to maintain it over a longer period of time. A very quick example here, this is a site plan for a house not built. It abuts to residential on one side, pasture land on two sides. It's for stormwater management, it's for irrigation and fire suppression. So we look at A, we have water coming overland from the pasture at the back, and already there is a drain, underground, subsurface drain, that takes that water out to the ditch along the front by the roadway. So that being interrupted there and then being carried forward to the front is kind of one area of catchment. Any overflow to that is captured and carried out to the front, straight to the storm drain, because it is surface water. But the ground level flow can go into the pond at the bottom of the picture there. Also going into the pond is some of the roof water from the back of the house. Section B up top is roof water collected in cisterns, and the overflow going into rain gardens at the front, which overflow into the storm ditch. C at the bottom is collecting rainwater off the roof, putting it into a vault. There is some overflow from the pond into the vault, but that is used for irrigation. And the overflow from that goes again into a rain garden at the front, same as the effluent and overflow from the A at the back. And that overflows into the storm ditch at the front. So in effect, really, there are 6 systems on this site. Starting on the left at the bottom, the runoff, overland runoff, is captured and carried through a pipe to the storm drain at the very front. Overflow, there is no overflow then because it's carried out to the front. It doesn't flow across the property, and stormwater flow that way is curtailed. But what soaks into the ground, because the finish grade is changed there and it creates some little berming, that water can go into the pond. So in the pond is a wetland area and a pond area. It's not a swimming pond. Water from the roof also goes into it, and it's great storage, and it's for fire suppression. Further down, off the back of the roof and off the front of the roof on the one end, goes into the buried vault. At the other side of the building, we have a cistern storage for irrigation. It's hidden here in this view. The cisterns then overflow into the rain garden at the front. And on the front rain garden on this side, which is overflow from the pond and overflow from the vault, those things combined. And further at the back of the property, I should say back from here, the front edge way behind us, the next residential lot, a rain garden for infiltration there too. So those 6 systems are all kind of individual and separate. But this is where it starts, at the roof. So when you look around, there's all kinds of different roof surfaces to deal with, some better, some worse, some not good, and we evaluate all of those in the training program. Same as we evaluate what is the reason, why are we doing this, as we did in the previous slide, what have we got to work with, where are we starting. There are questions such as, which would you rather have your rainwater come off of? What kind of roof is it that you look at? A roof has watersheds. These watersheds are all analyzed for volume and for quality and for suitability for what we want to do. In this particular case, this roof, the yellow ones face north, the green ones face south, purple faces west, and red faces east, only for us to evaluate. Every roof surface is sloped to go to a gutter. The gutter goes to a downspout, and only so much area can be handled by an individual downspout. So all these areas need to be analyzed, and the number of downspouts, their positioning, and their connection then into the rainwater system needs to be analyzed. This is part of the what. When we look at those connections in the gutters, gutter gardens, gutter soup, we look at scupper systems, we look at different arrangements of piping and how the water flows. We look at how these things are attached and what's existing, what needs to be repaired, what needs to be updated, and then perhaps what can be done, how things could work. In the center, that water wheel actually does turn when there's rainwater coming down the downspout. The one on the right is kind of whimsical. It goes into a rain garden. On the left, I'm not so sure about it. Why is that water at ground level just kind of sitting there? It should be probably going someplace, unless that's pervious pavement and it's soaking it up and taking it someplace. And then there are the anomalies. On the left, I've watched that downspout for 4 years, and it does collect a few drops of water every year. On the right is a real system, unfortunately jury-rigged, homeowner modified to lead into a cistern that is used for potable use only because there is no other water supply in this area. So we talk about the good, the bad, the ugly. We also look at climate and how it works with different formats here. We have in the top graphs and charts, we have a system that will meet 41% of the demand and a lot of red. The red means subsidized water. There is nothing left. It's using up everything that's coming off the roof, the 1,000 square meters, and nothing else is available. So there's a lot of need to subsidize. In the bottom one, we've added or quadrupled almost the roof area, and now we have some runoff or overflow, which is the darker blue. We don't have any red because we've met the volume we need, and we haven't really increased our storage by very much. Going through calculations like these are so important to give us a starting place to say, here's where we're starting from. Here's what we can meet, here's what we can't meet, here's how we can meet the demand, here's how we can fulfill the obligation of why we're doing this, and then we can start to say, okay, well, if budgets don't allow, let's maybe incrementally do this over 2 or 3 years or seasons and deal with the more pertinent details by having some figures and facts to work with. What goes into the tank? Very important. We can see the top left there quite clearly, the upside down T shape. That's a manner of slowing the rainwater down so it's not pushing on the base of the bottom of the cistern of the tank and stirring everything up. And we have also beside it a floating intake so that the intake is just below the surface of the water. In the bottom right, we have filtration coming in from the gutters, and that takes out leaves and other things like that as well. The bottom left is kind of what we try and avoid because it's just a spider web of lines and stuff that's going to get into trouble down the road. Being able to plan and design things ahead of time makes more sense. Here's a system that is for irrigation. So this is kind of the how now. This is the details of how things are going together. It's got 105 square meters. It's got 85% efficiency factor being a flat roof. It's a little, probably less efficient than it would be on a sloped roof. About 80,000 liters per year, annual, potentially. We need 19,500 for drip irrigation over 19 weeks. And so the optimum cistern size is around 5,000 liters. And you'll see 2 cisterns there in the image of the top right. The second is for future expansion of the irrigation area. This one here is for ice making. Potentially 3.3 million liters can be caught at a 90% efficiency factor, which includes 25% of the snow melt. With climate change, it's been recognized over the past 10 or 15 years that there are many more thaws during the wintertime, and that water can be utilized rather than it just being frozen from November until March. The annual demand is a little over 2 million liters, and 250,000 liters, 65,000 US gallons of storage is the optimum size. That means we could go less and have a little bit of subsidy, or we could have bigger storage, but there's no sense to go to bigger storage because we really don't need it for any reason other than perhaps emergencies, and perhaps if they wanted to add flushing to this in the future, then we could look at enlarging the cistern size. Another one in irrigation, it's got 90 square meters of roof capture, not the entire roof. They can capture with this part of the roof a little under 48,000 liters, and the annual demand is 57,000 liters. Now this property has no grass, all gardens, and a few chickens. So this is one of 3 tanks that will meet most of the demand in this particular area. The cistern size we need to meet that 57,000 liters, which actually in this case the maximum size we can go is 34,500 liters. There's no more overflow left. That's the biggest tank we could put on here. There just ain't any more water falling based on climate factors and climate data that we have. This is 100% potable, this system here. It's 114 square meter roof, 145,000 liters, 90% efficiency, a really nice new metal roof. Annual demand volume for the residents, 111,000 liters. And the cistern size, 26,500 liters. And that goes through a filtration into the tank with overflows. It is pumped out through a pressure tank and then through filtration, 20 micron, 5 micron, and UV light, and then into the residence. And from there, it is utilized in dishwashing, at the sinks, so the showers, laundry, and anything else they need to do. This is irrigation, emergency, and fire suppression. It comes off 185 square meter roof. Potentially, we can gather 167,000 liters. The annual demand is around 91,000 liters. That's for irrigation only. So we add to that, when we calculate that, we have to add storage for the irrigation, 45,500 liters. We had 5,000 liters for emergency. That means 1 week's worth of water for the house, which needs to be brought up to a potable level, but it has its own separate storage. Another 20,000 liters for fire. That's for 1 hour of fire suppression exterior to the buildings with large sprinklers specifically designed for firefighting that they can move around from different spots. This is a rural site, and it's prone in this area for summer droughts, and they want to be prepared for fire suppression as well. So a total of 70,000 liters of storage. Further on the how, things like pumps, and knowing whether we're using exterior pumps or internal submersible pumps or jet pumps, these different types of things, and who perhaps to get on the team who knows pumps, a pump supplier, of course, as well as other suppliers, people who supply the tanks and the other fittings and all the other paraphernalia that goes along with a rainwater system. That becomes the team. The team may also include engineers. It may include municipal people for permissions and those types of things as well. So the education and training is, I believe, proactively preparing and helping get ready before there are crises. When we look at the problems, we have to understand weather versus climate and how those things are different, and yet they tie so closely together. We have to look at infrastructure problems and why we are where we are and why problems are there and how we can maybe look at things differently in the future. We have to look at policies and standards and what's existing to say, can we do it better? With the issues, it's more than just I, it becomes we. And that's why the associations are a great place to be. That's why it's good to work in groups, and there are many, many, many small groups out there doing many things to set the best practices. Standards is the job of the associations. ARCSA has done that and is working on that, and so CanArm is bringing that to Canada as well, and working with other agencies along with it. We're bringing awareness, we're bringing education, training, and then the accreditation certification program that comes from ARCSA. We're distributing that and helping along here in this part of the country, this part of the world, to bring it forth and to make it really front and center. So the Accredited Professional is a 2-day workshop. It's open to anyone. If someone wants to carry on from there for accreditation, they need then to become a member of ARCSA, go through a written exam, and there's some other things that are more long-term there as well, including being able to prove that they're in the business and that they are up at the forefront of it with offering documentation of systems that are being installed. A design and construction program. It's a 2- or 3-day workshop, also open to anyone. The inspector specialist is a 1-day workshop with an exam, and it then gives a designation as an inspector. It's good for people who are already accredited professionals and perhaps are leaders in the industry as well. The Rainwater Harvesting Master requires the the accredited professional, the design and construction. It has a take-home problem to be solved, and then there is a special specific exam for that as well. There is a certification coming in 2017. There will be 3 avenues for it: design, installation, and inspection, done by a third party, ASSE International. That is kind of where I'm coming from. It's kind of the first step. It's kind of the initial thing. How do we go about doing things better? And these things are being offered across Canada and across the U.S. In various venues, in various places, and time frames. Our first one in this new format will be end of November in Burnaby, BC at BCIT, and more details will follow. We're still working on the very bottom details. In February, there will be some in Toronto area. So I think we've shown the value of rainwater harvesting. We've shown how it is specialized. It's not just walk into a store and pick up a rainwater system and take it home like you might with a lawnmower or something like that. Here's some contact information. I'm hoping that we've helped enlighten you a little bit on what rainwater harvesting is.